Hello, this is discussion number 2 for Calc 3. We're going to be solving this discussion problem if we have a surface given x squared plus y squared plus z squared equals a squared. Prove that every normal line generated from this surface passes through the origin. So I'm going to pull up my chair here. This is also being filmed on a new iPhone. Not sure how the quality is going to be, but let's see. We have our function x squared plus y squared plus z squared equals a squared. Well, what we're going to want to do is we're going to set this equal to 0 for reasons. Oops, that's not what I want to do. Minus a squared equals 0. So now we're given this a function. In terms of that's set to be equal to 0. We're going to make this equal f of x. F of x, y, z, that is, equals x squared plus y squared plus z squared minus a squared equals 0. 0 being our k for our level surface, I believe, I think. What we're going to do here is find our gradient. So we're going to have, I'm going to write it like this. F of x equals 2x. That's going to be 0, that's going to be 0, that's going to be 0. F of y is the partial of f with respect to y is going to be 2y. Because that's going to be 0, that's going to be 0, that's going to be 0, that's going to be 2y. Partial of z with respect to, partial of f with respect to z is going to be 2z. That's pretty much the same rule. And as a constant. So we have these functions. We're going to make our gradient vector of f of x, y, z. That's going to be 2x plus 2y plus 2z. Or if you really want to, we could put this in our 2xi. That's j. So x plus 2yj plus 2zk. So that's another way of writing our function. But anyways, we're going to want a point to prove this. And instead of just using a random point, we're going to use point that we can use with our symmetric equations or parametric equations. We're going to use point P. We're going to use P equals x initial, y initial, and z initial, or z naught. X not y naught, z naught. So now, with this, what we're going to do is plug in, do our gradient function in terms of our point. So if we plug our point in, we're going to get our, wait a minute, I just messed up here. What is that? Ignore that. No, I don't think you put commas between. I don't know what I did there. That was not the right decision. To z naught. And now we're going to, when we do this equation, when we find our symmetric equations and parametric equations, is that we have this formula, x equals x naught plus at. We have our point here, and then we have what we use to find a, or in case of other terms, y equals y naught plus b naught, or y naught plus bt. We solve our gradient, each factor of our gradient. So we plug in our point for x here, point for y here, point at z for here, or just our point in general if there's more than one variable in there. And what we do is we find that we're going to have our equation equal, or our function here going to be a, b, and c. Ignore the Vitamix in the background. So we might as well put our last symmetric equation or parametric equation up here. So what we do here is we found our AV. This is each if you think about it, our A is equal to our point here, B is equal to our point here, C is equal to our point here, except these points are our functions of x, y, and of x, our partial derivatives. So what we can do here is that we can plug in our function here, plus, and then we're gonna have 2x naught t, y equals y naught plus 2 y naught t, and the same thing for down here. And what we can also do is we can simplify this, so we have x naught plus 2x naught t. We can factor out our x naught, and we can get x equals x naught times, I'm going to go on the 4 for this, x naught 1 plus 2t. And we can do this for each one of our variables. We pretty much get the same function. So that's our functions, parametric function simplified. And if we really want to, maybe not. As I said, we could probably put this in our form of our parametric equations, but we already, well, over here you can. If you go over here, oh yeah, if you use this function over here, I'll do that last though, to show that our system is actually can actually go through the origin, a normal line. So what we have here now is that x is equal to x naught plus y plus 1 plus 2t. We can use our function, or we can plug in 0 for x, y, and z as something that passes, because it will pass through our origin. 0 is going to equal x naught times 1 plus 2t. And that's going to be same thing for here, as well as z. What we have here, the Vimex just stopped, by the way. So what we have here is we have our functions here equal to z, our function, our parametric equations, that is. What we know is that even in our x naught, y naught, and z naught are going to be equal to 0. And we can also, this is one way to prove it. Because we have 0 equals 1 plus 2t, 0 equals plus 2t, 0 equals 0 plus 1 plus 2t. This all equals 0. This means that each one of these functions is going to be equal to each other. That means, which this is going to equal 0, which all means it's all going to equal 0. But another way we can prove this, just real quick, if we could use this form of our function right here, we have x equals x naught plus 2x naught t. If we can subtract, we've put this in the form of our symmetric equations. We can do this for each one of our values. We get our symmetric equation right here. So if we plug in, so we want our function going through the origin, we set our x, y, and z equal to 0. We're going to get get our function equaling this. We're going to put this, let's put it right here. X naught over 2x naught equals negative y naught over 2y naught equals negative z naught equals 2z naught. I don't know why I put the naught up there. I'm doing all kinds of stuff today. That's a y, by the way. So if we factor, so what we can do here is that we can cancel out our x here and y here and our z here. That means, we're an arrow up here, we're going to get negative 1, 2, negative 1 over 2, or negative 1 half. It's going to equal negative 1 half equals going to equal negative 1 half, which means this equation. If we plug in 0 for this equation, that means it's satisfied. Thus proving that our normal line can goes through our origin. Not just one normal line, but every normal line that we have for our surface x squared plus y squared plus c squared equals a squared. That's it.